All right. My name is Melissa. I work for Rubin Observatory. I'm on the community science team, and Mario Yurick here is my co-chair for today. So we're going to be presenting to you first Data Preview 0 in general, and then we're going to focus on the latest data release. There will be a hands-on component. So if you want, there's some empty seats too, if you want to come and sit at the table so you can like work on your laptop in the second half when we do some hands-on stuff, please do feel free to switch if you want to. Reminder that we have a code of conduct. It's on the PCW website. Reminder to keep an eye out for those stickers on people's badges and for the social battery pins, and to use the email address listed at the bottom that you can't see because can I do that? Yep, that's better. This is a virtual session, so we have a bunch of people with us in the Zoom. They're all staying muted. But we will be able to ask them to unmute when it's time for questions. It's also the Slack space that we will monitor for questions as well. All right, just want to get started. I mean, I think I can skip this slide by now. You've been to the plenaries, you've seen the construction overview, the operations overview. You kind of know what Rubin is already. And then I wanted to introduce a bit the Rubin data management and system performance teams. These are the teams that are responsible for building, maintaining the LSST science pipelines and middleware, for processing, verifying and validating the LSST data products, and building the Rubin Science Platform for user data access and analysis. Instead of waiting for real commissioning data, which will be released to all data rights holders as Data Preview 1 and 2, these teams are providing simulated LSST-like data products for users now. And they're doing that in the Rubin Science Platform. Since when the data sets do come, it will not be possible to download the entire LSST data set. Scientists will need a venue for next to the data analysis. That venue is the Rubin Science Platform, or RSP for short. It's a set of integrated web-based applications and services that run at the Rubin Observatory Data Access Centers. The RSP itself has three main aspects: portal, notebook, and API aspects. And all of these aspects include tools to query, visualize, subset, and analyze the full LSST data archives in a stable software environment that's located next to the data, along with storage space, compute resources, and remote access options. So you don't have to put together any of that. You don't have to download software or install packages on your machine. You just log in to the RSP and it's all there ready for you to use. This is what it looks like when you go to the web-based RSP. The URL is data.lsst.cloud, but we will take you there later. And so now a little bit more about Data Preview 0. So this one, it's all simulated data. It's the first of 3 planned data previews between now and the start of operations. The specific goals for the simulated DP0 initiative is to enable the community to prepare for early LSST science with the RSP. It's to test integration of the LSST science pipelines in the RSP, and to use feedback on data products and the current RSP functionality to inform future development. We've got time between now and the first data release. So we want to get people in there using data products, using the RSP, and figuring out what works. The DP0 simulated data set so far has included LSST-like images and catalogs that were created by the Dark Energy Science Collaboration. They did this as part of their Data Challenge 2, or DC2. So if you hear about the DC2 data set, it is pretty much the same as the DP0.2 data set. It's just that when we call it DP0, it's those simulated images were processed by Rubin staff using an up-to-date version of the LSST science pipelines. So the timeline for DP0 was that in June of 2021, we released DP0.1, which was based on the DC2's data set and was processed by the desk. In June of 2022, so a year later, we released DP0.2, which was the same underlying simulations, but reprocessed by Rubin staff with more updated versions of the science pipelines. And now, just last week, we released Data Preview 0.3, which was simulated solar system catalogs that was simulated by the Solar System Science Collaboration. And they don't have images, but it is all of the catalogs that you would get out of the moving objects processing pipelines from LSST. And Mario is going to focus on what is in DP 0.3, how is it made, and how you can use it. So I do want to say a couple of things about DP 0.2. So it's still being served. We're still working on it. It's still very useful. It's not replaced by DP 0.3. Right now we have both of them at the same time. So if you want, you can, if you're an extragalactic or galactic scientist, you can get an account in the RSP now and just use DP 0.2. That's fine. It's still there, or you can use 0.3. So 0.2 was simulated LSST-like images and catalogs generated by the desk. They cover about 300 square degrees, and they used like a baseline survey strategy for the wide, fast, deep region. So there's no deep drilling fields in DP 0.2. It's just 300 square degrees of wide, fast, deep over about 5 years worth. The astrophysical objects that are included in DP 0.2 include galaxies with some realistic large-scale structure. There's type 1a supernovae in there, and there's variable stars. And there's non-variable stars as well. So 10% of the stars have variability in DP 0.2. There are both imaging and catalog data products that are in very similar formats to how the future LSST data will be served to users. So the imaging data products include the process visit images, so the single individual images taken in a given filter. There's deep coads, and there's also difference images. And the catalog products include, as they will in the future, signal to noise ratio greater than 5 detections and forced photometry in all of these kinds of images, in the individual ones, in the deep stacks, and in the difference images. You can find out more about the simulated data set for DP 0.2 at the URL that's down here in the corner, dp0-2.lsst.io. This is just sort of a picture of showing you exactly sort of where the DC2 images were simulated. It's in that teal patch there. And one note, if you haven't been interacting with DP 0.2 yet, the observing strategy that was used to simulate it is an old version. It's not, so like the most recent version of the observing strategy is like version 3.2. It's got rolling cadence in it. It's got twilight fields in it. The DP 0.2 used an older version of the baseline observing strategy. So if you are in there and you're like looking at the type 1a light curves, for example, and you're thinking, oh, it's a little bit undersampled. Yeah, it is, because it's an older version of the observing strategy. So it's not super realistic if you're looking at evaluating observing strategies using DP 0.2. That's all I'm trying to say. This is just sort of another example to give you an idea of the size of the DP 0.2 region with sort of a zoom in. You can see like the full field, the full area at left, a zoom in on like what we call one single tract in the middle, and then a zoom in on one patch at right, where one patch is like one CCD of the LSST science camera, to give you a sense of like the depth of information that's in these simulated images. Okay, so Mario's going to tell you about 0.3, but before we do that, I want to speak a little bit about how to get involved in DP0, how to get your account, how to use it. So if you want access to DP 0.2 or 0.3, you need an account in the Rubin Science Platform, which we've talked about already. And the exact instructions for how to get started involving going to dp0-2.lsst.io. The instructions are the same, whether you want to access 0.3 or 0.2. Right now, the instructions just still live in our DP 0.2 documentation. So you start there, and you can do this now. So if you don't yet have an account in the Rubin Science Platform, you can start this process. You can go to our Getting Started with DP0 checklist now. You can fast track your way. Start with number 2, submit a petition for a Rubin Science Platform account. If you get that started now, the steps are, it will ask you for some information like an email address. Try to use your institutional email address and use your actual institution as an identity provider. You do have options, like you want to log in with GitHub, or you can log in with ORCID, but it's easier for me, who has to verify your identity, if you just use your institutional email address and use your institutional affiliation for your account. So if you want to do that now, I can approve your accounts while Mario is talking, and you'll be able to log in by the time we do the hands-on part. So we can try that. And if you already have an account in the RSP and you want to start logging in now, that would be good. You can log in. You're going to use the notebook aspect, right, Mario? Yeah. So log in and start up a server on the notebook aspect now, and then you'll already be in there when it's time to go. Yes. So that's how you get started. Follow the checklist. These are all links. And if you have trouble, that's what our Slack channel is for. So you can use the Slack channel for this session right now, and I'll be watching for questions. Yes. Oh, you just pick medium for today. Yeah. Pick a large for today. Sorry. Mario says to pick large for today. Yeah. Good question. All right. So we're going to go through this checklist to get started with Data Preview 0. This process of getting an account in the RSP where you have access to DP0, this automatically makes you what we call a DP0 delegate. We've been using this sort of special term during Data Preview 0 it's kind of it's a special term instead of just user. You're a Data Preview 0 delegate. It just means that you have an account in the RSP, but we're using this special term because it kind of reflects the special role that you have now in the Data Preview 0 stage to reflect your role of representing the broader science community as our initial learners and testers and providers of feedback. And also sort of your role as you might be the only one at your institute right now who's engaging with Rubin Observatory and Data Preview 0. So you become the local expert, and now you can take what you learn back and share it with your local community. Accounts are currently limited to 900 people. We're just still ramping up. I'm sorry, the slide still says 900 and 600. But yeah, we're ramping up. There's spaces available, so go ahead and request your RSP account. And more people will be able to join as we approach operations. These are the two main sites for documentation. So at dp0-2.lsst.io, you'll find all the information I just told you about the DP0.2 datasets. You'll also find a bit of additional information about using the Rubin Science Platform, what you can do in the different aspects. And also in that documentation, we still have our virtual seminar schedule is there. We have information about where to get support. In our DP0.3 documentation at dp0-3.lsst.io, that's primarily focused just on the DP0.3 data set. So it's got a description of the simulation itself, and it's got the definitions of the various data products and tables that you can access. So those are the two things that you would be using if you're going to participate in Data Preview 0. There's plenty of tutorials for DP0.2 because we've had it for a year already. There's 2 tutorials for the notebook aspect now for 0.3. There's 2 more that are for the portal aspect so that everyone can get started, and then more are underway. So you're going to see more DP0.3 tutorials come out over the coming months as we get those up and ready. These tutorials cover everything from how to query the data, how to visualize really large data sets, how to display images and interact with them, how to use some of the middleware functionality that comes in the LSST science pipelines. We've got things about doing source detection, deblending, how to make light curves, all this kind of stuff that people will need for Rubin. We're starting to put in our tutorials. We also have virtual events. So pretty much every Friday, something is happening. Either it's a drop-in session that we call Stat Club, 9 to 11 a.m. Pacific, every other Friday. It's Stat Club, and that's a good place where you can drop in. If you're having trouble with something, it's a place to get help. Sometimes a small group of people will show up. So someone will come to Stat Club and bring 2 of their students, and they'll be like, we're trying to do this with the DP0 data. Can a Rubin staff member help get us started? And then we just get them started. So that's a good time to come. And then on alternating Fridays, if it's not Stat Club day, it's a delegate assembly day where we usually do something a little more formal. There's some kind of hands-on tutorial, maybe a presentation from someone who's doing science with DP0. And so we have that in the first hour, and then the second hour is more of a informal office hour help session. So it's a good time also to just drop in and share with us any troubles you might be having or any work you're trying to do. You can find all of the schedules for these virtual events at dp0-2.lsst.io. And next Friday, It is a delegate assembly day on Friday, August 18th, and that will be the first one on DP0.3. So if you're interested in the solar system data products, we're going to give an overview. You're going to get it today from Mario anyway. But you could get another one next Friday. What to do when you run into problems with your work. So there are a couple of options for getting support. So the first is the Rubin Community Forum at community.lsst.org. You go there, you will find a category that's clearly labeled support. And then there's a couple of subcategories in the forum, one of which is data preview 0. And that's for like literally any question you have, problems logging in, something about the data products that you're not sure what that means. If you find any place where we haven't documented something quite right, this is the place to ask. Literally any questions about data preview 0. We also have a GitHub issues option. If you like using GitHub and submitting issues, there's a support repository as well. And that's a good place to send like little bug reports, little things that you find missing, requests for new features in the RSP, that kind of thing goes there. Trouble logging in, you forget your password, that kind of stuff. All this little technical issues can go in the support repo. And we don't really care what you use. We just want to hear about the trouble that you're having. So it doesn't really matter what you post where. We just want to know what the issues are and to help you. This is a very handy slide of lots of links. I think this is pretty much, yep, that's my last slide. So I'll just leave this up and we'll do a couple questions before we have Mario take over. Oh, right, then we're going to do lightning talks. Then Mario's going to take over. Thank you.
Hello. Sorry if this was already covered earlier, but in the synthetic images, do you include fake asteroids and comets?
So there's no images associated with DP 0.3. It's catalogs only.
Oh.
And DP 0.2 does have images, but has absolutely no solar system objects. Yeah. Check in the chat for no questions. Any other questions about, yeah, Sam?
Is DP 0.3, does that include stuff from DP 0.2 or is it only solar system?
Only solar system and completely independent. So it's like a different observing strategy. And there's like literally nothing similar about the simulations. Yeah. Yep. But DP 0.2 is still available, served at the same time. Yep.
Yeah, I'll say a little bit more about that in 15 minutes, but the way to think about this is DP 0.2 is a simulation of what a data release would look like, whereas DP 0.3 is a simulation of what your prompt processing or prompt products database would look like. So it's you should think of those things as being side by side rather than one supplanting the other.
Can I answer any other questions for anyone? Okay. And if you've started your petition to get your RSP account and you end up with questions, let me know via Slack. We are going to have, I think, 3 flash talks from people who've already been working on Data Preview 0, just so they have a chance to share what they've learned and what they've worked on and to give an idea of the types of things you can do. These will all be based on 0.2, I think, because 0.3 only just came out. So let's see, we're going to have Bob and then Matt. Matt, you're going to speak to one. Yep. And then Jeff will speak. Okay. So our first one is going to be remote. So Bob, would you like to unmute and check your audio?
How do I sound?
You sound good.
Good.
Let me just get this into full screen mode. It's not what I wanted. Let me try again. Oh, I want this one. Yes. Okay, take it away, Bob.
Okay, so one of the things I did just playing around with DP0.2 was I looked at stellar classification. I used Brian Yanni et al.'s paper working with Sloan Digital Sky Survey data, and this right here is certainly DP0.2 data, but it looks very much like the Sloan data. And then in the middle, I did some modeling, some machine learning. And I really want to get into that more. This was just a simple polynomial fit, comparing, trying to predict temperatures based on Sloan Digital Sky colors. And then what I did was I didn't show this plot, but then I applied it to the DP0.2 data to see how it looked. And then finally, here is a DP0.3 image. This is our plot. This is, let's see, I calculated the diameter. It's just a histogram. I calculated the diameter of asteroids in a grouping. I think I took 1% of the total sample because it's a huge sample, just to see what it looked like. There's just a lot of stuff to play with, and this is really a good environment for getting familiar with the pipeline and the data set.
Awesome. Thank you, Bob. Thank you for doing that. Next flash talk, Matt. You need.
Okay, so I did this work with my students. Is this working? Can you hear me? Can you hear me? I can't. Pushing you. Ah, okay. Okay, so this is work that was done with my students, Anna and Armand. So this summer, we were at Fermilab trying to add synthetics, use synthetic source injection to add simulated kilonovae into DC2, the DC2 images through the Rubin Science Platform. So the image on the upper right there shows synthetic sources added. So I modified a notebook by Jeff Carlin that was written for DP 0.1 and used our models of kilonovae to try to add those in. We also were interested in trying to display a full square degree. So that's about 21 chips we wanted to display. So we put together a notebook to display multiple chips simultaneously. We called that Mosaic. And we also practiced with this thing we called Galaxy Viewer, different ways of viewing either a single calibrated exposure or a single visit image or a coad, and trying to also view a cutout together. So these are all things we worked on.
That is, Matt, is your stuff available like in a shared repo? Can people use it?
This is in the delegates. We pushed it to the delegates contributions. Thank you.
Oh, thank you.
Okay, so this is Jeff Carlin. In addition to contributing to many of the tutorial notebooks, I wanted to play around with sciencey ideas. So I'm interested in the stellar halo of the Milky Way. So what I did is, let's see, the bright colored plot, the leftmost of those two, you probably cannot see if you're in the room here, that there are these little narrow bands in those color diagrams. And those I surmised are blue horizontal branch stars. So then I developed a way to basically use those three different color planes to extract the objects within that feature. And then the great thing about blue horizontal branch stars is they're good standard candles, so we can get their distances. And so then I took those derived distances and then plotted the radial density profile of horizontal branch stars, which you see on the lower right in the Milky Way galaxy. And you see it extends out. I guess for those who aren't Milky Way scientists, the Milky Way should extend to about 300 kiloparsecs, and you see things extending well beyond that. And I fit the slope of this, and it agrees almost perfectly with what's expected. So just sort of a fun little science example of the types of things we could do.
Great. Thank you, Jeff. Let's thank all of our Flash Talk speakers. All right, now we're going to flip over to our DP 0.3 focused part. Stop share. No. Go.
Yeah, okay. Let me let me check if everyone can hear me. I'm usually quite noisy. All right. Thank you everyone for coming. So this part of the session will be about DP 0.3. I'll start with a short introduction on what is in this data set and why we built it and how we would like you to try it out. And then we're going to go and try it out. Before we begin, just to repeat what Melissa said, if you don't have an account, go to the DP 0.2 website that is in the Slack channel for this session. Click through the instructions on how to get one, and by the time I'm finished with talking about these slides, you probably will be approved and will be able to log in and follow along. Just out of curiosity, how many people do have an account on the RSP right now? Okay, perfect. So it looks like the vast majority of the room does. So if you do not have an account, it's even better because it means that Melissa will be able to help you out if you get stuck. So please do and go through that process. Before we begin, let me just acknowledge all the people who have helped build this. This was quite a team effort. The people I really like to point out are Pedro Bernardinelli, who is on Zoom, who has led the final stages of this effort and make sure that everything worked. Jake Kurlander, who's over there, grad student at University of Washington, who's done a lot of these simulations with Samuel Cornwall, who's also a grad student at UIUC with Siegfried Egel. There are a number of other people who contributed a lot of things, including myself, who have contributed by making these slides. The DP 0.3 data set it's been installed and made available on the Rubin Science Platform. We also like to acknowledge and thank the Rubin Observatory staff for putting all of that up there. That was also quite an effort to move all those data. We've got two more not really people to acknowledge, you'll see. First, we want to acknowledge Isha, who, for her critical role in ensuring the timely delivery of this data set. I will leave it at that, and I will let you ask me a question of why you wouldn't have the data set if it was not for this cat. And then the other person I want to acknowledge is our machine Epic, which has lasted for a wonderful 6 years and has allowed us to do all of this and then died 2 weeks later. So we thank Epic for valiantly getting these simulations done and then unfortunately expiring. It will be missed, but we will get a replacement. Okay, now let's get to business. So what is DP 0.3 and why do we have it? What we wanted to do with it was to simulate the expected LSST solar system data set. So to get a feel, both we internally and the community, of what will these tables look like, what are the sizes, and how to handle them. We're using it internally for pipeline testing to ensure that we're actually able to find these objects. And externally, and this is for all of us here, we've deployed it into the RSP so the community can test and provide feedback on how well the RSP satisfies common use cases. So with this data set, we would like you to go and try doing some of the science that you might have, that you may be imagining you would be doing with Rubin, and tell us what's the user experience. Does the notebook interface satisfy your requirements? Are the APIs good enough? Is the database schema, does the database schema look useful, et cetera? Any place, as Melissa said, where you either misunderstand something, or you feel there's no documentation, or you feel it just looks odd, let us know about it. We want to know about it now because now we have time to fix it, so that when the real data start coming in, you have a really good user experience. So that is the primary goal of DP 0.3 for solar system folks. What is in the data set? We have two data sets, actually, not one. We have a 10-year data set and a 1-year data set. The 10-year data set are all the asteroids and discoveries we expect after 10 years. So this is what you might expect at the end of the survey. At the end of year 1, the story is going to be quite different because we will not have discovered all these objects by then. And if you want to get a feel for your science cases, what is the world going to look like by the end of Rubin's year 1? This is a better data set to look at. So 10-year gives you the sense of sort of where the whole thing is heading. What's the maximum? 1 year gives you a sense of what to expect soon. The caveat with the 1 year, though, is that the assumption is this is 1 year done under the assumption that we'll have templates from day 1, which, as you've heard before, that will not be the case. We're going to be doing incremental templates. So there's going to be some hit in our ability to detect sources. So that's the caveat. These are probably upper limits. We're using baseline 3.0 cadence. We've done mock linking with realistic losses. So our requirement is to find 95% of all the trackers that we can link. So we've thrown out 5%. We have realistic magnitudes, astrometry errors. We have absolute magnitude fits, and the whole thing has been loaded into the RSP. And again, this wouldn't have been possible without a lot of community developed software from both folks in the solar system science collaboration. There's been tremendous work in the UK, Meg Schwab's group at QUB in Belfast, and including other software, including folks from JPL and elsewhere. What are the inputs for the simulation? For the solar system model, we're using S3M. This is a fairly old model by now. So this is Gravital 2011. It was, I think, built originally for Pan-STARRS. For comets, we use the model put together by Mike Kelly and co-authors that's on this URL. For interstellar object, we use a synthetic population that Ari Hines developed. And then we have some Easter eggs that we're not going to tell you about, but we're going to ask you to find them yourselves. These are objects that move unusually, in unusual ways. All of these have been combined with the MPC orb, so with real data. And done in such a way to create what we call a hybrid input catalog. So that is an input catalog that has real objects on the bright end. And then as we go towards the faint end where objects are not known, it switches to simulated objects. So if you want to learn a little bit more about how that is done, go to this URL. These slides are available on this session's page, so you can go ahead and find it. But the key point is that if you look at the macro level, these catalogs all, the hybrid catalog and let's say the MPC orb and S at the bright end and S3M at the faint end, they have same statistical properties. So same absolute magnitude distributions, same orbital parameter distribution, et cetera. So the idea with these hybrid, with this kind of construction is that we will know which objects we are just seeing again. And we will not be rediscovering things like series and counting that as a Rubin discovery. So that's what this enables us to do. Known issues. It's very important to understand that this is not a data set that is perfect. And there are a number of known issues that we've known going into this, and then there are issues that we're discovering as we're exploring the data set. Again, I want to point out, I want to stress that the primary purpose of this data set as it is right now is for us here to test the Rubin Science Platform. So to test how well can we use these databases to make queries that will lead us to our science, not necessarily to predict the numbers of objects that we're going to discover. So do keep that in mind. a couple of things to point out. One, the data set is for most populations missing U and Y bands. We've cut those just to make sure that the database team has enough time to just load everything in. Those may be added later. U and Y, as you know, are not bands in which we observe quite often, so this is not a huge loss. Our color treatment is very simplified for these objects. So there are no complex SEDs here. There are colors of something that looks like an S type and color, and all the others are C types. So there are just two color classes. The MPC org table, that's one of the tables in the database, does not have a semi-major axis entry. So this is more of an annoyance rather than a real miss. You can take you can compute it from Q, take Q and divide it by 1 plus eccentricity. But this is something that we're going to add. This is one initial piece of feedback. And then the most interesting bit is that the number of total detected objects is about 4.4 million, and the number of observations is smaller than previous simulations. So we're trying to understand that why. This is the first time we run a simulation at this fidelity since baseline 1.7. So we're trying to understand whether this is a combination of changing the baseline, or whether this is something just with how the data were processed. In the meantime, the LSST has switched to a bit more realistic as measured assumptions for the limiting magnitudes. So I take these numbers with a grain of salt. We're going to know in about 2 or 3 weeks exactly how much to trust them or not. Again, this is in the spirit of us trying to put this out more to test the RSP than to go and make predictions about what the LSST is going to be able to deliver. The key point here is that if you notice a problem, please discuss it on communitylsst.org or report it at this GitHub repository. Melissa mentioned a number of other repositories where you can raise issues. That's fine. If you don't know exactly where to raise an issue for which particular thing, just open it anywhere. We'll make sure that it gets to the right place. Okay, so here is where I'm going to pause for a second, see if there are any questions. And then once we go through the questions, we are going to go and have some hands-on fun. But while we're going through the questions, let me just urge everyone to go ahead and log into data.lsst.cloud, because depending on how many of us try to do that at the same time, there may be some time delay until all those machines become available of a couple of minutes. So go ahead and do that, and I'll pause and take any questions. Oh, sorry, there's one in the room. Yes.
The 5% of linkable objects that you say you throw out, does that mean they're not in the data set, or they're missing a flag that says that you linked them?
So it means we, every opportunity where we have 3 tracklets that are in the right configuration to be found, rather than just saying, oh, this means that object was found, we roll a dice. And in 1 in 20 times we say, oh, this object still hasn't been found. But what happens is, for the vast majority of objects, we have many opportunities to find them over and over again. So it turns out that efficiency or of 95% is actually doesn't impact the total score, if you will, that much. We don't keep the sources that we do not link. So we only have, this is a simulation of LSST. So things that are not have not been identified are not there. Correct me if I'm wrong. Yeah. Meg, go ahead and unmute.
Thanks. I just wanted to say first, it's so exciting to see this on the Rubin Science Platform. So thank you to everybody who's made this happen. on behalf of the Solar System Science Collaboration, because this is a game changer in being able to test our code and really understand how to work with the Rubin Science Platform and notebooks and the whole ecosystem. So thank you to everybody who's involved in making this massive effort happen. I wanted to ask about the Easter eggs. So say you think you found one, how best do you go finding out if that's true without spoiling it for others? What's the best way to send you an email, Mario, or send a message to the CST? What's the best way to check that you found the weird thing or the weird things that you've implanted?
Pedro, do you have a preferred way of how to hear if people found strange objects?
It's a good question. I guess you can ping me or Mario, and we can tell you if it's a real Easter egg or not.
So but we have to set some rules of the game for Easter egg hunts. We weren't quite that good at hiding them because they all have names. So all these asteroids have some designations. And if you're clever, you're quickly going to figure out that some have names that look different than the others. So if you want to play this game fairly, don't look at the names of the objects. You can look at the names at the end, and that's probably how you can figure out yourself if you found it or not. There are no prizes, so you know.
Could lead to naming things for the prize winner.
We can name the simulated object after you. Oh, that's what you mean. We should talk. Okay, any other question before we head into Jupyter Notebook land? All right, let's go do some queries. Okay, so I will, let's see. Test. Okay, so I'll try to drive from here and speak close enough to the microphone to be heard. So first things first, make sure to go to data.lsst.cloud and log in. And if you do that, the first time you do that, you're going to be asked which instance or what size of machine do you want to be given, and please select a large one. I think medium is going to work as well, but large is just going to make your lives easier. Before I continue, let me just see how many of you have reached this this part or in the process. So you're able to log in. Okay, and who's still trying, just to get a feel for where I should wait a bit? All right, I have confidence in Chris. So once you're there, let's get a copy of this data set of these simulation notebooks onto your Jupyter Hub accounts. So I want you to type git clone https:// github.com/lsst-sssc LSST simulation. And now I see that is super tiny, so let me see if I can make it larger. It indeed is. And if you missed the moment when I opened the terminal, I opened it by clicking on that terminal icon. If this is all new to you. So let's see if I manage to do this without any typos. Oh, incredibly so I did. So if you do the same, you should get these couple of lines of progress from Git. But what will happen is if you click on this little folder icon, again, to refresh the list of folders that you have here, you should see an LSST simulation folder appear. And just to make sure that most of us have gotten there, let me see by show of hands, we're there. We're still working on it. Check for typos. That's usually when that happens. And Jake, if you can help out, if it's not a typo, it's something else. Oh, and Jeff put it in the slide, so copy pasting will also do. There are many S's. Yeah, I think if you push it up and to the right, it'll be fine. All right. Okay, so let's all go into the LSST simulation folder and then into notebooks, and then you're going to see two notebooks here. This one here is from an internal release we did with the Solar System Science Collaboration in 2021. So do not open this one. It actually won't work on the RSP. Open this one that says Solar System Sims 2023. And then here's the notebook. There's some introduction. I want to say before we begin with this notebook, Melissa mentioned that there are going to be a number of tutorials. There are two already that are in the tutorials directory. They're quite longer than what we have time for today. So this notebook here is sort of a distillation of what you're going to see there, with a lot more explanations and a much more kind of pedagogical written out explanation of what's going on. So if you don't understand what or if you miss some part that I'm going to do here, you can go and take a look at those notebooks for some extra details. But this one is us trying to cram those 2 to 4 notebooks into about 20 minutes worth of a demo. So assuming we're all here, we're going to start by the way you're going to start working with the DP0.3 dataset and virtually any dataset in the RSP is by instantiating what's called a tap service. This simply run this cell. What this does is it creates an object that you can use as your gateway into the database. You can ask this object to run queries for you, to get you data, etc. And an example here is, here we're going to run a simple query to just see what are called schemas are available. And these are roughly equivalent to, let's say, different data releases. I'm massively oversimplifying things, so please don't jump on me, those who know the details. But if you run this query, you should get this output out. And the two things I want you to notice are this one and this one. So DP0.3 catalogs 10 year, and DP0.3 catalogs 1 year. So these are kind of self-explanatory what they are. In this namespace are the 10-year catalogs. In this namespace are the 1-year catalogs. And we're going to see in, I think, the next line exactly how we use them. So each of these namespaces then has tables. And we can run another query to find out what tables are available in a particular namespace, a particular schema. So I'm going to run this query. It says select table name description from tab schema.tables, where tab schema.tables.schema name equals this name that we've discovered up here, and then order by table index. This is not strictly necessary. Let's say table name, so that it's sorted alphabetically. So if you run this cell, what you're going to get is you're going to get a list of tables that are available. So let me talk you through them. MPC orb is the orbit catalog. We might name this differently in the end, to just name it something else, but this is, or to, no, actually we won't. This is likely to be named MPC orb in the future. because this is going to be the orbit catalog that we download from the Minor Planet Center. To remind you how the way Rubin's asteroid discovery is going to work is we take images during the night. In the morning, we do the linking. When we link objects, which means effectively discover them, we send those objects to the Minor Planet Center. The Minor Planet Center will check our submissions and incorporate them into their database, aka MPC orb. And in the evening, we download that MPC orb and load it into the database. So this MPC orb table here is meant to be that Minor Planet Center database that we will be loading on a nightly basis, including, and it'll be including objects that we've discovered as well. Right now, you'll see that a lot of the cells, a lot of the columns in that table are not populated. And the reason for that is they're just simulated objects. So we don't have the details like when was this simulated object first found, or those types of things. The other objects are, so MPC orb is a table of orbits. Attached to that table of orbits is this SS object table. So if you imagine an entry in MPC orb, for those of you who are working in solar system science, let's take Sedna. For Sedna, MPC orb is going to have an absolute magnitude. It's going to be an absolute magnitude in the V band. But what Rubin is going to be able to do is going to have so many observations of that object that we're going to be able to compute our own absolute magnitude, not just by using some very rough conversions to the V band, but in each individual band. So we will be doing those things, and we will be storing those object-related quantities that we compute in this SS object table. So this SS object table is effectively a one-to-one map with the MPC orb table. You can think of it as extra columns to add to the MPC orb table. So these are objects. Now let's talk about sources. The DS source table is a table in which we hold all the detections detected on difference images in Rubin. When Rubin is on the sky, that table will hold, as I said, all the detections, not just solar system objects, but any difference image and any source that was detected on difference images. In this database, because this is just simulation of the solar system, we only have solar system objects in the table, but still we have the same schema as will be used in operations. And then this SS source table, for those objects, for those sources that we know come from asteroids, because, for example, we've linked them, and now we know that that's a moving object. We can compute additional quantities of interest that are not found in DS source table. So in the DS source table, probably isn't quite useful to specify both the heliocentric distance and the topocentric distance to every single quasar. But for solar system objects, it is. It makes some queries easier. And this SS source table is where we add that information. So SS source table also has a one-to-one map with the DS source table. You can think of it as extra columns to be appended to the DS source rows if those rows are solar system objects. So this has been a very long explanation and me just talking a lot over a lot of text, but I hope that it's given you at least some idea of what these four tables are, because these are kind of critical things that where all the data, basically all the data lives. All right, let me pause here and see if there are any questions about this. I'm going to run a couple of queries through these tables, so you're going to get a feel for what's in them in just a minute. So that may help as well. All right, if not, let me continue. So let's run a query. Let's ask how many solar system objects are there in the SS object table. So this is how you run queries with TAP, service.search, and then you type in the your query in here. This query is in a language called ADQL. ADQL is a superset of SQL or SQL. If you know SQL, you know probably most of what you'll need for, well, you know everything you'll need for this tutorial, and probably most of what you'll need for solar system objects in general. So this on my machine took, or when I ran it, it took about 3 seconds, and it came back with about 4.4 million SS objects. So let's run the same query against the SS source tables to see how many observations are there. So one of the things we're actually testing here is how well the database scales. Because when I ran this, it took it took a certain amount of time, but now when we all start hitting the database at the same time with the same queries, I think it'll be interesting for the team to go and look at those logs and see how well it did. So this took about 10 seconds and came back with about 650 million observations. So for the reminder of this demo, you'll notice that we kind of, all these queries look the same. It's service.search, then you give it a query, and then we run .toTable to convert it to AstroPy table. And because because I like pandas, I also run a .toPandas to convert them to pandas. So what I'm going to do is I'm going to wrap all of that boilerplate into one function called query. So that's what this does. So make sure to run that. Because then what I can do, make sure to run this, is for the rest of this tutorial, I can simply say query and give it a query, and it'll return a data frame with the result. All right. So now let's run a couple of queries for these 4 tables. So here's our DS source table. You can see what's in it. There's a band of observation. There's a visit ID, declination. There's a right ascension somewhere hiding here. There are magnitudes. There are magnitude errors. There are also columns that will not exist in the real catalog. Anything that you see that has the word true will not be in the real catalog. These are true values from the simulations. For example, true declination before we mixed in the error and so on. So this is a nice way to test certain things. So this is also a good way to see what's available in these tables. And if you see something that's missing that we should be doing for your science case, first check the official data product schemas to see if that column is present there. Not all columns are included here because some of them haven't been simulated. And if the column you're interested in is not present there, let us know, and we will we'll see if we can add it. So let's do the same thing for SS source. Again, SS source adds interesting quantities that are relevant for solar system science to each DS source. So here's ecliptic latitude, ecliptic longitude, heliocentric coordinates, many other things. Notice some things haven't been computed for this simulation. That's all in the all can be visible here. Let's do the same thing for SS object, and then let's do the same thing for MPC orb as well. As I mentioned, the MPC orb entries that come from the simulation don't have everything that you see in present day MPC orb catalog. And I'll end this small tour of various tables by running this query. What this query does is it will tell us how many observations per band are there available in the catalog. So let's see how long this will take. When I ran it on my own, it took 18 seconds. It still takes about 18 seconds or so. So as I said, we have G, R, I, and Z bands, and U and Y bands we do not have except for a few objects. I think these are the Easter eggs. So don't look for Easter eggs in U and Y. Wes. Because it's from an S3M input catalog, and we just didn't compute it. Yeah. In the SS object catalog, though, you should see an arc. Sorry, in the SS object table, I think there's an arc column that is correctly filled out. Melissa.
Is there a documentation on the column labels?
There is, let me just try to find it.
My question was, because it has several columns regarding the MOID, and I was wondering if that was with respect to Earth or someplace else, some other planet.
With respect to Earth. Yeah, I think we only compute MOIDs with respect to Earth. So the place to go to for the schema. Okay. Probably can't write this down, right? We have a schema in a nice Google spreadsheet format. The way to find it is if you go to ls.st/ssp, that will take you to solar system processing pages on Confluence, and then at the bottom of that page, you'll find this link to the schema. Another place to find it is there's the official schema browser as well, right?
And you can use the portal that exposes the whole schema.
Okay, so let me continue just to make sure that we get through the most important bits here. So this here was just a quick demo of what's available in various tables, but now let's try to do something more interesting. So here's an example of a query that grabs observations of all solar system objects observed in some night, and I picked semi-randomly MJD 61004. So if we run this query, this should take about 5-6 seconds. This returned a data frame. In this particular night, there were 182,000 asteroids, 182,000 observations of asteroids. Let's plot them. So what I did here is I'm just using matplotlib scatter to plot RA versus DEC. And this is the sort of thing I get. So you get the wide, fast, deep, and you get this lone and lonely deep drilling field with many, many objects. All right, let me pause here and make sure everybody reached this point. Yes. All right, so the next thing I'm going to do is I'm going to ask in that night. Now I want to find one visit, and I want to find one visit that has many asteroids. So what I'm going to do is I'm going to take that data frame. I'm going to group it by CCD visit ID, which are exposure IDs effectively, and I'm going to count those values, and I'm going to sort it in a descending fashion. So this gives me what this means is, for example, for this CCD visit ID, there were 1,800 SS objects in that visit, or 1,800 asteroids. For this visit ID, there were 1,500, and so on and so on. So this is, if you're new to this, this is kind of an explanation of how pandas and pandas-like tools work, how data frames work. It's very convenient and quick to get these kind of summary statistics out. But what I used this for was to find one visit ID that I'm going to go now and select. I'm just going to ask for data for sources from that visit ID, and then I'm going to plot them. So that's what this next query does. I'm going to run that. I'm going to plot it. And then here is the result. So this, if you squint, you should be able to see that this kind of looks like the LSST field of view. In this simulation, we've included all the effects, including vignetting. So there are going to be, there should be fewer objects at the edges and things like that. So that should all be visible. This should be a very interesting thing to look at. But so what I wanted to do is I wanted to show you how quickly you can get to this type of data set. If you want to just give me all observations from this point, from this pointing, this is the query that will get you there. But then what if you want to plot this not in RA and DEC, but in ecliptic coordinates? Well, you can actually get that information from the database itself by making a join of the DS source table with the SS source table as shown in this query. So if I just run this and make a plot, here's that same field, but now these are ecliptic coordinates. These are lambda and beta. And as you might imagine, this is much closer. This is relatively close to the ecliptic, which is what you would expect for a well-populated field. Now, one thing I'm going to point out is that this is quite an electronic mouthful to write this join. There are tutorials that the CET team has put together to explain how to write joins, how to join together tables. And if you're new to SQL and ADQL, and this is the first time you see it, I'd really encourage you to go there and familiarize yourself with how to do this. And we're going to have tutorials with more join magic or explanations of how to write these things soon. The other thing I would like to ask everyone is, I look at this, and on one hand, I wonder, I'm at awe how the database can do all this for us. On the other hand, I look at this and think, oh my God, that's so much text. So these are the kinds of things or impressions that we would like to hear from you as well. If you find a certain thing to be incredibly tedious to do or to write, or you find yourself always be doing this join between dia sources and dia objects, tell us. We may be able to do something on the database side. We may be able to produce what are called views or somehow simplify these queries. So because what I'm trying to say is, just because this query looks complicated, doesn't necessarily mean that we cannot simplify it. Sometimes a complicated query cannot be simplified, but sometimes it can. You just tell us for everything that you feel like you're writing boilerplate over and over and over again, just ask us, like, can you do something about it to make my life easier? We really would appreciate that feedback. All right, so that was just a quick example of how to grab individual visits and a demonstration that there are visits in the data set. Now I'm going to go and get a whole month worth of data. So first thing I did was to go and find out when the survey started. I asked for the minimum midpoint MJD TAI, so the minimum the first source that was recorded in this data set. And then I'm going to go and ask for all sources between that point in time and 30 days later. So this is now going to take a little bit longer. So this, when I ran it, and it was just me on the system, this took about two minutes. So let's hope it will still take about 2 minutes. But in the meantime, this is a great time to pause and see if there are any questions while we're waiting for this query to return. Oh, yeah. Oh, Kat, you're here. Do you want to ask the question?
Oh, the one I put in the Slack?
Yeah.
Yeah, it's just about the orbital uncertainties. This is not a thing MPC provides, which is incredibly frustrating as a dynamicist. So I would love, for example, I'm writing software to do dynamical characterization. I'd love to be able to query that out of Rubin data, but MPC doesn't provide that.
So MPC you'll be happy to hear that they are changing that.
Yay.
And we already have access to their internal tables that have all the uncertainties. They're switching everything over to OrbFit. So
excellent.
And they're recording everything that OrbFit puts out. So uncertainties, correlations, it'll be your life will get much better.
Excellent. So will we get another data preview at some point with those?
I'm not sure if we're going to get a full data preview, but we'll certainly get it in operations. That's the table.
Yeah, I would just need an example of how to like API query that.
Oh, sure.
Awesome.
And
I think they do covariance matrix. Yeah.
Any other questions? My clock hasn't run out yet. Were there any more? All right, let's see. Let's see if this will come back in the next few seconds. So what you see here is, as you might expect, if you ask for a single visit, you're going to get an answer quite quickly. Once you start asking for more and more data, it takes more time for the answer to come back. So in this case, I asked for a month worth of data. So that should be on order of 600 visits per night times 30. So that's 18,000. visits. So that's the difference in scale. And I'm going to be patient. I'm going to give it another 30 seconds to a minute. But while we're waiting for that to end, to finish, this is going to be the output once it does. Is there anyone who started this before I did, and where it did it finish already on your end? 10 seconds ahead of you. Who's running it right now? Oh, okay. And how many of us are running it at the same time? I just want to get a feel for how much we're hammering the database. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Fritz will love to hear this. All right. So let's just let it go. It was not an intentional frozen reference. Oh, it's done. There we go. So it finished for me. And let me run it. Yeah. And we got the full month of observation. So these are the time scales that you should expect from RSP. I just want to point out, like, this is a full month of Rubin observations. To get that back in something like 2 to 3 minutes is not a bad thing. Now, if you were actually doing something with this, and you could do all kinds of things and analyze these objects depending on what your science case is. But I want to switch gears a little bit, and instead of focusing on how do we get lots and lots of observations for a certain period in time, I want to now show you how to get observations for a single object. And here, please don't run these cells before I tell you, because there's one that takes a long time, and I want you to skip that. Wes is smiling in the back, so it's probably ran everything by now. Okay. So what I want to do is I want to pull out data for one asteroid and plot a phase curve, or get the data out that are required to go and fit a phase curve. So, oops, I'm actually not sure why this is here. Let's just skip this part. So what I'm going to do is, if I want to fit a phase curve for an asteroid, what I would love to have is I'd love to have an object that's actually been observed over a wide range of phase angles. So this is what this query does, and please don't run it. 2 reasons. One, it's quite a complicated query. What it does is it takes what it asks for, what it selects is an ID and the band in which the object was observed for an object where it selects an ID band and then the difference in the maximum phase angle the object was observed in and the minimum phase angle the object was observed in. So I'm looking at the difference between the maximum and minimum, and what I want for a phase curve is I want that difference to be large. So I want something that was observed at both large and small phase angles, so that there's a large range there. And I select this from DS source joined with SS source. You can look at this in detail and decrypt this query. It's grouped by each individual object and the band, and then I order it by this range of phases in a descending fashion to get this output. So this gives me an object, for example, this one that's been observed in the Z band at 127, almost 128 degrees worth of differences in phase. That's what I wanted to do with, that was the goal and the idea with this query. And again, if you look at it, if you look at the execution time that I had when I ran this before we all jumped onto the RSP, it took about 7 minutes. So that's why I'm asking you not to run this, because it will take a lot longer now. But, so say again?
I actually did run it because I just hit, it took 6.5 minutes. So even with all of us on.
Because I can't run the rest if it sticks for long.
Dangerously.
All right, I'm going to give it another 20 seconds and then I'll stop because I helpfully pulled out the number that we all care about into the next cell. So you can just run the next cell without running this one. There are 64-bit numbers, but the database hates unsigned integers. So they're stored as signed integers in the database. So some of them are going to have minuses. You shouldn't attach any meaning to those numbers. They're just opaque identifiers. Okay. Someone here can just leave this running. I'm going to stop it so we can move on to the next cell. I apologize to my notebook. Python stack traces. It's awesome. All right. But in that previous run, one of the objects that had a lot of range had this SSO ID. So then what I do with this query is I just pull out its name. So that's 2014 QL4. So in this simulation, we would have really good measurements of 2014 QL4. And now here's a relatively complicated query that I'm not going to go into the details of explaining how this join works. Again, if you know joins, you'll be able to understand it. If you don't, I think this is a longer tutorial, unfortunately. But what I want to show is that when I run it, I get back all of that information that I need to plot a phase curve. So I go and do that, and here they are. So what I did here is I actually took all the magnitudes and then where did I do that? And I distance corrected them before plotting them. So that's what this does. So here's how the brightness of our asteroid changes with the difference in phase, and you see the kind of behavior that you would expect from a real object. And sorry for the folks who are not solar system or acquainted with the solar system work. When we talk about phases, think of the phases of the moon. Depending on where you are or on where the asteroid is relative to the Earth and the moon, you're not going to be seeing the entire surface of the asteroid illuminated, but you might be seeing a smaller fraction of the surface. It's literally just like moon phases, and then that causes a fall in the magnitude or in the brightness of that object. But it's a little bit more complicated than just the surface area. It also that fall in brightness is modulated by surface properties, including the roughness of the surface, etc. So if you're able to measure how that brightness changes as a function of phase, you can actually learn a lot about what the surface material of that object looks like. So that's about 2 weeks of explanation in one sentence. So I apologize in advance. It's case insensitive. I think this is actually against our. This is my fault. I think it should be. We're trying to encourage people to use capital S and then I think lowercase s. I'll defer to Melissa what the right standard is. So think of this as a typo that will be fixed, but it does work. It's just a convention on that we. What do we prefer in terms of naming of different tables? I think it's capital D and then lowercase ia and then capital S and then lowercase source.
Does that work?
Oh yeah, it does. I mean, because it's SQL is case sensitive. And Gregory, if you're online, if you heard the question, you can also.
I did not actually hear the question.
What's the canonical capitalization for various tables? Do we have?
So I'd have to look to see what the DPDD says. But in the what's actually on the system is capital D, capital S for DS source, and capital S, capital S, capital S for SS source. Right, so it's because solar system is being treated as an acronym, whereas DIA is being treated as a word. So that's not very consistent since they're both actually acronyms. But that's what's on the system right now for the table names.
Thanks, Gregory. One place where that does matter is, so SQL itself is case insensitive, but Python isn't. So if you name your column mag or lowercase mag, the AstroPy table that you get back will have a column that's also named all lowercase mag. If you name it capital M mag, then it's going to have capital M mag. So that's why it's kind of good to look at these conventions and then abide by them, because that will make it easier for us to share code. All right, so here's our data for the base curve. We can also grab our age and G1 fits for this curve, and then we can try to overplot them. But if we try it right now, this is going to fail, unfortunately, because there's one component that we need to add to the RSP, which is SBPy. This is it's just a piece of software that I think we'll add it once it goes through the process, the RSC process, and then we'll be able to run these kinds of experiments on the RSP fully to the end. So let me pull up this older notebook to give you a sense of what that result would look like. You would get something like this. So now, of course, with real data, this is what you're going to be able to do on your own, and then go and find unusual objects and etc. And that is it. That is all we wanted to show. There's this last cell that we can run that gives you a sense for what the input population looks like. So what this does is it takes all the data from the MPC-ORB table, which is effectively the S3M model plus the MPC-ORB catalog, and plots that as a function of magnitude. You're going to see all these spikes. And those are just because of how the S3M has been constructed using fairly coarse bins in absolute magnitude. So it is, you can compare it to the plots in Tommy Grau's paper. But this is just a quick demo of how you can do binning with SQL as well. So this is all we wanted to show you, all we have time to show you for now. The idea here is to make sure you're all able to go and run these notebooks. Let me see how many of you have been able to do it. Okay, excellent. That's about like 10 to 15 people who have gone through the whole thing. To give you a sense how to run this, to give you a sense how to access DP0.3, to give you a couple of queries that you can now go and copy and paste and modify. That's why I wanted to give you both a query that brings in a lot of data and then a query that picks out one object and brings in all the data for that object, to give you enough to get started with. And we hope you're going to use it. We hope you're going to try it out. And I especially hope that you can give us feedback for everything that you find intuitive, that you find it works well, and then all the things that you found counterintuitive or hard to understand or just slow. And we'd like to take these next 2 years to figure out how we can improve that. So when real data start coming in, that we're all ready. So I'll stop here and open it up for questions for either Melissa or me or anyone who's spoken so far. Okay, Pedro, do you want to tell the story of the cat?
Yeah, I can tell it. So we were trying to wrap up the data preview, and I put some things to run in our now dead computer and went to bed, and my cat wakes me up at like 2 a.m. To ask for food, and I decided to check what was going on with the code processing and etc. And it turns out the code had crashed like 10 minutes after I went to bed or something like that. So thanks to that, we actually finished things in time. If he woke me up at his usual 4 a.m. or 5 a.m. to ask for food, I think I would not have tried to debug what was going on.
Yeah, so we were on a tight deadline, and we used all the help we could get. All right, let's leave it. Yeah, depending on how much how patient you are, I'm curious when it will end. All right, any other questions? If not, thank you very much, and just like a big round of applause for this entire team that put this together. I think this is a really big effort, and thank you for coming, and thanks to the team who built it.